Anyone poke into Harvard architecture? Maybe look up examples of computer systems, specific examples of computer systems that make use of the Harvard architecture. Has anyone bothered to find out that? Okay. I thought people would actually go a step further and look for specific examples, right? Try and understand how the thing works. Did you? What? When you hear during the discussion of the von Neumann architecture, the introduction, not the last, yeah, the introduction. So the introductory class is where we had our discussion of, we touched on this notion of there being additional architectures besides the von Neumann architecture that are somewhat different. We really just highlighted the Harvard architecture because it happens to be one of those popular alternatives that people talk about, right? Even though we know that there's probably plenty of... Is that fine? Yeah? Can we see at the back? Okay, so then we continue off with our discussion of you notice that this is a relatively, is that fine? All right, so you notice that this is a relatively short lecture series. Like I mentioned last time, ideally, we were supposed to have merged it with lecture series number 5, but it turns out I think it's a lot easier to explain things when you split them up. So this is specific to the CPU. Specifically, we are really only interested in trying to better understand exactly how the CPU executes instructions, right? Okay, so we proceed. Okay. Now, I was wilding out when I was updating these slides. I'm thinking, because of the tutorial things, maybe we should at some point have a review of the quiz. I'm not sure. The solutions are shared on the Moodle, but what I'm thinking is, and this is part of what I wrote about in here, I think. What I was thinking is, because this tutor thing seems to be a very contentious issue, right? I don't know, apparently it's registrar and whatnot hasn't yet signed papers. So I'm thinking instead of us waiting, because we've covered a lot, what I'm proposing we do is we allocate one of these funny days, perhaps a Friday, where if people have concerns, we'll quickly run down the quizzes and maybe have some, I guess, modified version of what would be our tutorial session, just so we can have recitals, if you will, of what we've covered so that people understand or something. I don't know. But just as a reminder that the test is actually after next week, right? So we want to pay particular attention to this. And what we are planning to do is on April 12th, which is Friday next week, we will have a quick review of what we've done, just to get a sense of what to expect, right? Sorry? The venue hasn't yet been confirmed. We haven't yet confirmed that, but it's after next, I'm reminding us that it's after next week, right? Sorry about the lab sessions, but it's not my fault, but I apologize again for the confusion that was there on Wednesday. All right, great. So on with it. So our lecture series is as follows. Just a brief introduction to remind us of the link between the von Neumann architecture and what we're going to talk about, and then this will mostly be focused on the interaction between the functional units, which we know by now, right? ALU, control unit, the input-output unit, or the input unit, output unit, and the memory unit, right? And remember that the control unit and the ALU are what make up the central processing unit, right? And also we know that within the central processing unit, there are other components besides the control unit and the ALU, specifically the registers, right? What else? What else is important within the CPU? Buses, right? Buses. Right. And then we'll just look at the instruction cycle. It's a short cycle, right? Fetch, decode, execute. That's it. Trying to understand what goes on there. And then we'll look at just one example of how this is done. Just a simple program try and explain it, summarize, and that's it. I think we have enough time to finish. So here's the thing: the so-called, our so-called conventional, not classical, but conventional polynomial architecture is composed of these units, right? And we know what they do. But fundamentally, what we're saying is that what this component does, the central processing unit, of course, in conjunction with the control unit ALU and the registers, the buses, is it executes program instructions, right? Instructions, individual instructions that are associated with computer applications that you would have executed or loaded into memory or RAM, right? I'm running Ocular right now. As I am using this application or manipulating the data, in this case the slides, there are instructions associated with Ocular that are being executed by the central processing unit. Individual instructions associated with this application called Ocular, this thing here, complex application, yeah, similar to Microsoft Word or Adobe Acrobat Reader. Right, so the central processing unit is responsible for the execution of these programs, right? So essentially, what happens as you're executing these instructions is you go through a loop where you have your programs that are programs loaded into memory, right? Your program is loaded into memory, and the individual instructions are fetched from memory. Instructions associated with the program, they are fetched from memory by the CPU. Instruction finds itself in the central processing unit. At some point, it has to be decoded because the CPU needs to figure out exactly what to do. When the instruction is fetched from memory, it has no clue what it needs to do, right? So there has to be a mechanism in place to identify the specifics of the instruction that has been fetched from memory. So the control unit is there to decode the instruction and say, oh, we need to add, oh, we need to move contents in this memory location to that location, right? Oh, we need to jump from this memory location and go elsewhere, right? And then once the instruction is decoded, obviously things I'm explaining, like, oh, we need to jump. The jumping part is what forms part of the execute phase, right? So fetch, decode, execute. And then optionally, trying to emphasize that at some stage, once you're done with this cycle, right, potentially data would have to be stored back into memory, right? So you send the data back into memory, write it into memory. All right, and obviously this only just performs arithmetic unit, right? So, right, just to remind us again, right? Like we said, so the processing happens in these three phases here, right? Step 1, step 2, step 3. Always you start off by fetching the instruction is decoded, and then the instruction is executed. And then you loop, right? You fetch, decode, execute. Fetch, decode, execute. Right? Everything is happening at a very fast rate, right? Remember we brought up this notion of the frequency at which the CPU oscillates, right? Things like 2.5 gigahertz, right? 2.5 billion instructions in a second, right? That's a lot. I mean, that's even hard for a human being to kind of comprehend here. Apparently, I was reading somewhere, and there's supposed to be CPUs that execute instructions at a rate as high as 6 gigahertz, right? That's super fast. So interesting things happening in the world at the moment. Now I sat down because I need to be somewhere closer to the mic. Wow. Okay. Right. So specifics about these individual steps, right? So we're fetching the instruction. So the first thing the central processing unit will do is it will make use of the control unit to try and check the memory address that is sitting in the program counter, right? When everything is initialized, the program counter will have a memory address loaded into it. And remember what we said about the program counter, it's nothing more than a register, right? So it sits in the CPU, it's a temporal storage location, right? So it checks the instruction that needs to be executed, and then copies that instruction to the memory address register, right? Still on the CPU. And you notice here, the moment we're talking about things like memory address register, once that instruction is copied, the copying entails that because we're talking about memory address register, once it's copied from the program counter to the memory address register, it goes through what? The address bus, an address bus. It has to be an address bus because we are dealing with addresses, memory addresses, right? pay particular attention to the different types of data that we're going to be talking about here. Right, so once that instruction, that address is copied here, and there's a step here that it's still executing here. Yeah, so the instruction is going to be placed in the current instruction register. That's before it's executed, right? We go into detail on what exactly happens here. But it's copied in the current instruction register because the execution itself only happens, instructions are only executed once they're placed in the current instruction register. Right? Right, and then obviously the control unit to decode that instruction, right? To try and figure out exactly what's happening. And I want to again mention up front here that the description here is not as realistic as things actually happen. You notice that we are again abstracting things. So when we are walking through the fetch decode cycle of specific examples, you notice that we're omitting certain steps, right? So bear in mind, just don't say he said this but that. We're abstracting things here. All right, so control unit needs to decode the instruction to try and figure out what to do with the instruction. Should I add 2 operands? If I'm adding 2 operands, then the control unit will immediately know that it's expecting what? Potentially two operands and an operator. Well, the operator is add, obviously, it's expecting 2 operands because it's a binary operator, is it? You add 2 numbers fundamentally, right? Yeah. And then you execute the instruction, right? Optionally, in the event that you are manipulating data, for instance, once you do your execution, you obviously have to store the result of whatever operation you are performing, add or subtraction, back into memory, right? Right. So remember our discussion about how these instructions are formatted, right? We said fundamentally we have different types of instructions, if you can call them that, right? There are instructions that are understood by the computer, so-called ones and zeros. There are low-level instructions. This is the lowest layer that people such as ourselves, programmers, have access to, right? This is the lowest level that you have access to. And then we have high-level language source code, right? So things that we can really intuitively understand, right? We read var result is equal to, we know exactly what's happening. It's not always clear as to what might be happening here if you don't understand assembly language, for instance, right? This is a lot easier to understand. So we are reminding ourselves that usually, depending on what type of language we're dealing with, the conversion could be either from here to here, from here to there, or direct from here up to here, like Python, right? You are translating individual instructions associated with this high-level programming language into machine code, right? Or it could be an intermediate, I guess, output if you're dealing with a language like Java, right? So you have bytecode, which is further translated into machine code, right? So back to the point I raised to say we are simplifying things. You see, if you look at assembly, for instance, when we say we are adding these 2 operands and then we are storing the results into here, this is what we are doing here, by the way. It's not as simple as that, right? What we are effectively doing behind the scenes here is this operator that we are calling add here is mapped onto, it's mapped onto an opcode that is a direct, that is directly converted into machine code, right? Now, I deliberately put up this slide to show you what the equivalent of add is, which is 0, this hexadecimal number 00. And we're using, again, we're not using ones and zeros. If it was ones and zeros, because it's a hexadecimal value 0, it's just what? This would be just like 6 zeros, I think. Because the bit pattern of the, this is MIP, so the bit pattern of the opcode has to be allocated 6 bits, right? So just emphasizing the fact, play along here, I'm just emphasizing the fact that we are simplifying things here, but in actual fact, behind the scenes, this has to be converted into a form that a machine will understand, right? And specifically, this is what we mean, right? So in case you're interested in what the conversion is all about, I mentioned this notion of an instruction being one word long. So you have 32 bits, right? Those 32 bits for each individual instruction like this add the contents of 8 and 9 and put them in 10, for instance. These are translated into 32 bits. And then at some stage, obviously, once you're executing the instruction, the CPU will be fetching the 32 bits, what? 1 byte at a time. So it's 8 bits at a time. So even though this add $10, or add the contents in register 8 and register 9 and then put them in register 10, even though this instruction looks like this, but we know that it's 32 bits, meaning that the CPU, once it's fetching this instruction from memory, it won't fetch the entire equivalent of add, $10, $8, $9. No, it will come and fetch the first 8 bits, and then the next 8 bits, and then the next 8 bits. As it's doing that, when it goes back, when it fetches the instruction and then pushes it into, could be like the MBR or MDR, what the control unit will do is it will check this bit pattern, is it complete, right? So it checks these 8 bits. This doesn't look like it's complete because it knows that when it sees a bit pattern similar to this, it automatically knows that this guy or this instruction wants to add, right? If this guy wants to add, then I'm expecting more things to come, right? So it will go back, fetch the next 8 bits until the instruction is complete, and then boom, executed, right? It was simplifying things here. Just thought people would want to remember here. Again, program counter keeps track of the next instruction that needs to be executed, right? This will help us understand the examples. The memory address register keeps track of the memory location that is currently being read, right? From memory, main memory, which is RAM. And then the memory buffer register or memory data register. Some books will say MDR, not MBR. It's one and the same thing, right? So the memory buffer register or the memory data register is the one that's going to hold the data that is being fetched from memory. So once CPU checks the address in the memory address register, let's say it finds address 1000, it will go and check what is in 1000. Once it finds what is in 1000, it will fetch what is in 1000, and what is in 1000 is what will be put in the MBR or MDR. Two different things. There is the address, and there is the things that are located on that address, right? It's located in two different things, two different locations. In this case, registers. And then the current instruction register is the one that holds the instruction that is currently being executed, the thing that you're going to execute, right? And then finally, just again, control unit decodes the thing that has been fetched, right? The instruction that has been fetched from memory. Then this thing performs arithmetic calculations. Now, so assuming we have this sort of scenario where we have this simplified program, right? It's in assembler, obviously. And it's not any assembly language that you find out there. We've simplified things again. If we were using MIPS, we would have used different instructions. But to help us understand, we're just saying, we're assuming there's the load instruction, right? That loads contents from memory, right? And then there's the add instruction that just adds things up. And then the store instruction will just write things to a specified memory address, right? We're simplifying things here. I'm not saying there's nowhere where you find this, nowhere, right? So again, let's assume that our so-called byte addressable memory is located like so. So at memory address 100, we have this instruction loaded. At memory address 101, we have this instruction. Remember, if this is a program, once you run it, it's loaded into RAM, right? So we've loaded it into RAM. It is here. This is our RAM, our main memory, yeah? And then 102 stores that, right? And then let's again assume that we have actual data located in these memory addresses as well. 103 has the value 1, 104 has the value 9, right? So the question is, what exactly happens behind the scenes? We said the first thing that happens is initially, the PC will be initialized by the next instruction that needs to be executed. Like in this case, we're saying the next instruction that's going to be executed is located at memory address 100, which is the load 103 instruction, right? So pay attention to the red text here. So PC program counter is pointing at memory address 100, which is the next instruction to be executed, right? What happens? We're saying the program counter, this is fetch cycle, right? What the contents of the program counter will be copied will be copied into the memory address register, right? So we are saying we are copying the first instruction. The next instruction we're executing is 100. We're going to copy this 100 into the memory address register, right? And you notice that 100 is pointing to what? This instruction, right? So in memory address 100, we have this instruction. So once we copy the address, CPU knows that, oh, okay, so the instruction is located at this address. The contents of that address will be fetched. Once they're fetched, because we are now dealing with data, it's instructions, obviously, data and instructions stored in the same location, we must move the contents into the MBR or the MDR. Right? The moment we move the contents to the MDR, something interesting happens, right? Observe. We said that the PC has to be now initialized to what? It has to be incremented by 1 so that it points to the next instruction that is going to be executed. We haven't finished the fetch decode cycle, but at this point of the fetch cycle, the moment we load the contents into the MBR, it will point to the next instruction that we need to execute after we're done with this. And again, we are simplifying that. It's not always when we are done with this process. The concepts such as pipelining, that try to, again, ensure that the CPU is efficient. So you run things in parallel. You're no longer dealing with a single cycle, single CPU cycle. Say, before we execute this instruction, we must wait until it's done. No, right? With pipelining, you do things in parallel, right? So you can do other things. Of course, there are problems associated with that, but I digress. So we copy the contents of what is in MAR. What is in MAR is at address 100. What is in address 100 is what? Load 103. So we copy load 103 into the MBR and increment the PC by 1. Once we do that, still in the fetch cycle, we must now move what is in MBR in the current instruction register, because the CPU only executes things that are in the current instruction register. So we again copy the contents of MBR into current instruction register, right? And then once we copy the contents into the current instruction register now, the control unit comes in to try and figure out what exactly this load 103 is all about. What must I do, right? What must CPU do? Right, so you decode. It knows, oh, okay, the load instruction simply means I must load the contents on address 103, right? I must load them somewhere, right? Because it's a value, it's going to find itself in the accumulator I explained just now. You notice, address 103 has a value 1. We said load 103, this is an instruction. Once control unit decodes the instruction, it realizes to say, I must load a value where? In address location 103. So, which is why we have the 1 here. This is the data now, right? So the data, obviously, this 1 is going to be pushed into the MBR, right? And then copied into the accumulator because it's data. Now, notice something really interesting, this whole notion of the stored program concept, right? I'm going to double back slightly a few slides. Observe the contents of the MBR, right? Previously, we had what? An instruction, right? At some stage, we found ourselves what? With data, right? Memory and data stored in the same location. Are we following through? Yeah. Don't worry, it will make sense soon. So we decode it. I'm sorry? Yeah, but we incremented it at some stage. Look at, pay particular attention to this number. Yeah. Yeah, the PC.
What's the use of it? Why should it be implemented to 10?
Because Good question, thanks. Because you see, we are going through this so-called instruction cycle. We just don't run one instruction. We're going to be running the CPU whenever your machine is on. It's always executing things behind the scenes, always, all the time. This is why this thing is making funny sounds here. The things running behind the scenes, the instructions being executed. We are going through what? And a cycle of executing a ton of instructions actually associated with different programs, because I have processes of applications running in the background. It's not just Ocular that I'm running on this machine. There are other things running behind the scenes, right? So the reason we're doing that for the purposes of our example is we have 1, 2, 3 instructions. This load, this add, and this store. So once we are done with executing load, there has to be a way in which we're going to execute add. How are we going to do that? We must point to where add is going to be located, right? Boom, 101. So we are...
So it just adds 0.
Yeah.
Because the computer like it's 1 and 0, so it only adds 1.
Not really. It adds a 1 because addressing in memory is contiguous, so it's continuous. So when you add 1, you get to the next memory location. And we're simplifying things here again. It's not, we'll get to it once we look at the ISA architecture. But for now, let's just say when we add 1, the moment we add 1, we find ourselves at the next memory location, right? Okay. So fetch decode cycle for this load instruction is completed at what point? Once you execute the instruction. The things that are in red here, we're decoding, we're fetching, decoding, we execute. Once we execute, we are done with the first cycle. But because our program is made up of 3 instructions, for the purposes of this example, we're going to have to cycle 3 times, right? So the second cycle begins. We copy the contents of the PC into the memory address register, which is 101, right? The moment we do that, the next stage is we try and fetch whatever is contained in 101, which is add 104, right? And then obviously this is going to move through the address bus, right? And find itself in the MBR or the MDR. But then something interesting happens, right? Previously, the PC initially it was initialized with memory address 100. Once we go to the first instruction, the moment we execute that, it incremented to 101, right? And then once we copy, in the next cycle, once we copy the contents of the MAR into the MBR, boom, it increments by 1. Because once it's done doing these things here, this processing here, it must execute the thing that follows next in line, which is at 102, store 105, right? So we increment program counter. So you notice that we are repeating what we did here, but different instructions. Same process, different instructions, right? Again, we're still fetching here. We load the contents in MBR, which is this instruction that says add 104, right? So we need to now move these or copy the contents of MBR to the current instruction register. Again, we need to copy them to the current instruction register because the CPU only executes things, it works on things that are in the current instruction register. Once we move them to the current instruction register, the control unit comes on the scene to try and figure out what exactly must we do here, right? So internally it figures out, oh, what do you know? We must add whatever is in 104. Observe what is in address 104, the value 9, right? So it knows a couple of things here. It knows that our accumulator had a value of what? It has a value of 1. It still has this value of 1. It says that we want to add we say add 104. It knows that, oh, this guy wants to add whatever temporal processing we have, which is 1, we add 9 to it, right? So it decodes that instruction, adds 9 to it. And then the contents of the accumulator will now be 10, right? The value 10. We've added 9 to 1, which is 10. So in the execute cycle. And then we go back now, because we have our simple program has what? 3 instructions. So we must cycle 3 times. Now, applications like Chrome have thousands of instructions associated with them because you do different things with Chrome. You can save a web page. You can access a URL location, right? Different things there. Different things imply there are a ton of instructions. Now we must go and Google up as homework how many instructions associated with Chrome, right? You'd be surprised. It won't come in the exam, but it's nice to, people think there's a pattern here. I guess we might say. So in the next fetch cycle, we are saying, because this was 102, we copy what is in 102, which is store 105, right? The moment we do that, increment to 103. Now I have to say this up front. There's a bit of a mishap here. Ideally, the addresses associated with the data were supposed to be on different memory locations, because even though this is our final instruction, what this might imply, people might get confused, say, oh, maybe the next instruction to be executed is 103. No, this is data, not instruction. But it doesn't take away a process we're going through here. So same process, we copy the 102 to the memory address register, right? And then we go to memory and fetch whatever is on 102 and put it in the MBR or the MDR, right? It's instruction here. And then the moment you do that, PC is incremented by 1. It must point to what has to be executed next. And then what is in the MBR is going to be loaded in the current instruction register. Again, processing is only done, like processing here is saying decoding and execution is only done on things that are in the current instruction register, right? This is slide 44. Slide 44. Slide 44. Great. So we move that into the current instruction register. And then the CPU now, again, has to decode. What is this instruction all about? What must we do, right? And then it realizes, oh, it's a store instruction, meaning that we must save whatever processing we did, whatever is in the accumulator must be saved into memory, right? And then you notice that we are specifying where we are going to store, because it's a store, we are writing to memory, we need an address, right? So the store is followed by this address. So we're going to write whatever is in the accumulator into the address 105 in memory, right? So the value 10 is going to be written into memory at address 10. Does that make sense for these hypothetical things? Three-step, our simple program that only does 3 things, right? And by the way, the 3 things we're doing is we're just adding things and then storing them into memory. Is that fine? Why? Oh, what? But why? Why? Oh, farewell. We are done actually. Okay. It's a summary really. So we are saying this to summarize everything. What say PC will store the next instruction, and then it's going to be moved. The address of the PC is going to be moved to the MAR, and then PC will be incremented. And then contents will be loaded into MDR or MBR. Finally, they'll be moved to CIR. And then PC will be incremented. Well, PC has already been incremented by 1. C will decode instruction to make sense of, to figure out what's actually what will have to be done, right? And then the instruction will be executed, right? So to sum it all up, I mean, this is what we are going through. We are looping through these 3 different phases here: fetch, decode, execute, optionally store, which is where the fetch, decode, execute cycle name comes from, right? Right, so some things to pay particular attention to really is the different stages involved. The special purpose registers that we just described, PC, CIR, MBR, right? MAR, the accumulator as well. So we must be able to explain what these different special purpose registers actually do. And then I just wanted to leave us with this to give us a sneak preview of what's happening very, very soon. You see, we've simplified things here. But in actual fact, what's happening inside is so complex, right? So we shall, once we look at the data path and control as part of what we're doing for the computer architecture part, we shall trace these instructions, exactly what is happening, and we'll be tracing the ones and the zeros really. Again, it's a simple instructions, but trying to understand what is actually happening to this instruction, right? Because we said this add instruction, if we're talking about MIPS, it's actually, this is equivalent, the equivalent of an add instruction like this is this. So we'll be tracing how exactly does the CPU figure out, what to do when it sees this bit pattern, and what is pretty interesting in my opinion anyway. Are there any questions with regards to what we've done today?
How do you access your lecture theory, your lectures on YouTube?
You go on YouTube. No, that's a joke, right? Oh, okay. Is that it? Yeah, is that it? They're not mine, they're ours, right? Come on. Now, there are even voices of people asking questions like here being recorded, hopefully. Please, let's us switch on these things when we're asking questions. But anyway, so that because the recording here, for people that are further away, I only have this small mic, so if usually if there's the audio is audible enough, I can pick it up. All right, so you just go on YouTube, and then, in fact, the YouTube channel, the specific section that has these things, you notice that there are playlists there, right? Playlists associated to the different things that we are covering. Those playlists have short little videos. They have short videos, not short little videos. They have short videos, short video footage that is related to the things we are covering. And these are by no means comprehensive, but these are things that I've come across that I think will be helpful in trying to help you understand the things we are covering. So you want to pay particular attention. Maybe I can show people what I'm talking about here. Probably not. You want to pay particular attention to those things. There's also a playlist that has the recordings themselves. So like this screencast has been recorded if you want to refer to it, I guess, for whatever reason. Anyway. Yes.
Sir, on the illustration, I think let's go back to the illustration.
Yes, sir. The illustration. Okay.
For fetch, decode, and exclude.
Okay. Which instruction are you interested in? The add, the store, or?
You jumped 98 and 99, then went to straight to load 10.
Which 98?
I didn't go back again.
Can't find 98. Where is 98? You are looking at old slides, sir.
But you're the one who put them on the Moodle.
Well, so I shared them. These slides are always changing. The reason we put them on Moodle and the web profile is because if there's any change, it's a reference. It would be different if I printed it out. If I print it out, you will never see the changes, right? But if I put them on that location, every time you visit that location, when you notice that there's a change, the moment you go and check, you find that the slides have been updated. The reason I updated them is, if you look at the slides that you have, the explanation was a bit obscure last time. People complained that it wasn't clear enough. So I thought this illustration of walking us through what you're reading doesn't have these tables showing us what's actually happening. People found it hard to understand, so I thought this would be slightly helpful anyway, which is why it's different. So there's no 98, but it doesn't matter whether it's 98, it's just a memory address. It could be 1,000 for all we care, maybe a million or something, not a million, but.
Yes, sir. Yeah.
Yes.
Yeah, on the main memory. This side is 100, but why are you loading 103 when this side is 100?
But we are loading what we are specifying to load. We are going to load what is in 103 because we are saying we must. What is in 103, for instance, is we are loading what is in 103, which is 1 here, because the instruction says we must load 103. Load the memory address 103. That's what we're saying. Rephrase the question. Maybe this is. Rephrase it. Come on, let's do this. If you are busy, it's fine.
So you mean those numbers?
But because this is a query session, so if you have to rush for class, it's fine. But I think we'll stick around because these are interesting questions that people are asking. By the way, we shall freeze the class theory test until this point in time. So the test will be up to this lecture series 6. So right from 2 to 6. Yeah, so question, I just wanted to, but we mentioned those details. Yes?
If you can go back to that.
Okay, I wanted to show the YouTube thing. Okay, sorry.
So you mean these numbers which are, is it the left side? So you mean they're just a number of instructions?
No. So what we have on the, again, we are simplifying we are simplifying this memory view, right? This is just like, it's a schematic to help us understand. In actual fact, memory is actually not loaded like this. And you notice once we have a discussion of logic gates, right? It's the discussion of digital circuits in our introduction. You notice that memory is nothing more than, it's made up of just circuitry that controls the flow of electricity. That's how simple this is, right? So what you have on the left-hand side are the addresses, address locations. What you have on the right-hand side, this load, add, store, 1, 9, are the instructions and the data. We said both instructions and data or data are located in the same location, in memory, in RAM, right? The location is, memory is what? Byte addressable. These things are located in like chunks of like 8 or something.
You said
so,
memory is what?
Byte addressable, that's what we say.
What's that?
Well, a byte, again, so a byte is just 8 bits, right? So we're saying in memory, the way that things are stored depends on the type of memory again, but for purposes of what we're doing. The things are stored in chunks of 8 bits. So when you're pulling things from memory, what you're doing is you're pulling 8 bits at a time. When you're going through this fetch, decode, execute cycle, and you go and fetch things from memory, you're doing it 8 bits at a time, right? Because you're doing it 8 bits at a time, and I'll have to go back here. Because you're doing it 8 bits at a time, for an instruction like add $10, $8, $9, which is one word is 32 bits. For something like this, even though we've simplified things when we're going through that fetch decode cycle, we just said the add is going to be fetched and whatnot. In actual fact, what the CPU is doing is it will go through, when it's performing an add instruction, for instance, because it's 32 bits in size, right? One word long. It will start fetching parts of this instruction, 8 bits first. And when it fetches that 8 bits, it's actually going through like, that's the actual fetch decode instruction cycle that we're talking about. So when we're saying the fetch decode cycle in this case involves just the load and the add and the store. No, the add itself, because the add is made up of 32 bits, we are going through 4 cycles within the add instruction. Cycle number 1, fetch these bits.
Those first bits are stored in what before we go to the add? Those first ones, where are they stored?
These?
Yes, where are we fetching them from?
The MAR.
The MAR. Then the add also has all 32 bits.
No, so this is part of the add, by the way. This example of our add.
Also,
This actual MIPS example of the add, and in fact, this is an actual translation. This is MIPS. This is a MIPS assembly code instruction for adding, right? One of many versions for adding. There's 3, I guess. So the equivalent machine code for this, the things that the computer sees is this. The computer actually sees this. In fact, right, it's really interesting. A typical program, right? If we were to write a simple assembly language program, what the machine will do actually is it will see a series of 32 ones and zeros, 32 ones and 0 bit patterns, say 2 ones and 0 bit pattern, a whole bunch of them, right? And then it plays around with that. And you notice that these bit patterns are quite important really because there has to be a way in which a machine knows to say these 32 bits associated with this instruction. And when we get these 32 bits for these instructions, the first 2, 4, 6 bits associated with the operator. This is how it knows that if it sees, like for MIPS, if it sees 0000000 with a combination, by the way, and the func code, and we'll get to that, then it knows, this is an add instruction, and then it's going to add it. But we're simplifying things just to understand the fetch decode cycle. We are abstracting. Gentlemen, ladies, I'll see you when you see me, which is Monday, bright and early. We have a class, but we must start studying for the test, right? Thank you. See you. Oh, unless if there are other questions, probably not, right? I apologize for the confusion with. It's not my fault, but I have to apologize. The lab and the power in the thing. I apologize.